So work, of course, is the way that we change the energy of a system. By exerting a force as an object moves through a distance, energy can either be given to the object or taken away from the object, positive work or negative work. But there are special types of work being done by conservative forces where the amount of energy that is given can be sort of taken away again, or vice versa, by simply reversing the process. So if I move an object from point A to point B, or maybe from an initial height to a different height, the process of moving it back again to its original position, if that process reverses the flow of energy, then we consider the force that's acting to be a conservative force. And gravitational forces, great example of conservative forces, where the energy change back and forth is reversible. In this case, when you have a conservative force, we can define a potential energy. And of course, we've been talking about potential energy along the way, but it doesn't have to just be gravitational potential energy. There are other types of energy that can be stored, and then that energy can be taken back again, as long as the force that was acting during that change of energy is what we call conservative. What we mean by, again, a conservative force is that if, say, in the example shown here, if I have an object and for whatever reason, whether it's being lifted or it's thrown and so it's just moving upwards, but if it moves from a low position to a high position, if it moves in the positive direction, but there's this negative force of gravity acting on it, if we were to calculate the work done by gravity, it would be a negative value. We would take mg as our force, delta y as our change in position or our displacement, but because those directions are in opposite directions, we pick up a negative sign. So the work being done by gravity would be negative. Energy is being taken away from that object. But when the object comes back down again, then the force is pointed in the same direction as the motion, and so there's no longer that negative sign. It's a positive amount of work. The energy is given back again. So one of the ways we can talk about the effects of gravity is we can follow this work idea, or we can talk about the energy being temporarily stored as potential energy. So the negative work that's being done, taking energy away from the object as it goes up, that energy is stored as what we call potential energy, and then when it comes back down again, we get that energy back. You're very used to talking this way because we've been doing it for quite a while. But again, it doesn't have to just be gravity that does this sort of process. For instance, later in the year we'll talk about springs. And the spring force is also a conservative force. If an object is attached to a spring and it stretches the spring, here it's moving to the right, so it's stretching the spring away from its equilibrium or its relaxed position, that's going to require energy to be taken away from the object, because the spring is going to be pulling to the left, trying to work against that object's motion. The displacement is to the right, and so the work being done would be negative. It turns out that it turns out to be negative 1/2 kx squared. Little k, you might remember, is called the spring constant. Again, we will talk more about this later. I'm just trying to give you another example of a conservative force. When the object moves back again to the left, like it does here, the displacement now is in the same direction as the spring. The spring is pulling it in that direction, and so energy is being given back to the object. That's positive work being done. Again, though, this is a reversible process, and so we can talk about that energy being stored as potential energy. What we notice, though, is that the change in potential energy is opposite the amount of work being done. So if a force does negative work, taking energy away, the potential energy goes up. It increases. And so the amounts are the same, but there's a sign difference over here. Not all forces, of course, are conservative, otherwise we wouldn't bring up the term. Friction is definitely a non-conservative force. It's not reversible. If I take an object and I slide it across the table to the right, there's a frictional force pointing to the left. And so if I wanted to calculate the work done by friction, I would take the force of friction, mu times the normal force, times the displacement, and then there would be a negative sign because those two the force and the displacement point in opposite directions. If I switch now and the object comes back to the left, well, friction also switches. And so the directions are still opposite. The work done is still negative. It's not reversible. I'm not getting that energy back again. So we cannot describe or invent a potential energy dealing with friction. So where is this going to be used? Any force that is defined to be a conservative force, something where the energy can be taken and given away in a reversible way, we can define a potential energy function based on that force. And to do that, we would think about calculating the work, which would be the integral of F dr, and then taking the opposite of that work value, and that would tell us the change in the potential energy. If our potential energy wants to be, you want to write it as an actual function, then you would do that as an integral and include a constant value added when you integrate, and that constant value would be the initial value of potential energy. So the two ways you're going to see this is you might be given a force function, like here, negative 8x squared minus 4x, a force value, a force function in terms of position, and then you might be asked to determine the potential energy function. So you would integrate it, and in this case, the potential energy is 3 joules at x equals 0. So that would be your constant term that you add when you integrate. Or you might be given a graph of force versus x, and if you find the area underneath that graph, or between the force graph and the x-axis, that's going to almost match up with your potential energy, except it's going to be the opposite of it because of that negative sign. The area would tell you the work, and the potential energy change would be the opposite of that. The other way to look at this is to flip that integral around. If u is the negative integral of f dr, then f is the negative derivative of u with respect to r. And so if we're given a potential energy function, like this one here, 12x squared plus 5, we can determine a force function by taking the derivative, 24x, and then multiplying by negative 1. Or if we're given a graph of u versus x, we could look at the slope of that graph. And whatever the slope is, if we take the negative of that, it would tell us the value of the force at that particular position. So these are our key calculus relationships that you need to be aware of. The key connection is understanding that the work being done by a conservative force is equal to the opposite, or the negative, of delta U, the change in potential energy. And so we can define a potential energy function by integrating, or we can define a force function by taking the derivative of the potential energy. Please note that these particular relationships are not on your formula sheet, so as you work through the practice, try to do the questions without looking back at your notes.